Okay, so it is detection and attribution of climate change, and this is certainly one key element of climate science born in Hamburg. And I'm talking about work done by Klaus Hasselmann, Eduardo Zurita, Aminé Bakhordarian, Armin Bund, and Jonas Bent. And so the graphics I'm showing are from Michael Schenk. So it is our third seminar here. And so we had already two. And the first two have been recorded and have been placed on YouTube as part of the TRR channel. And so we have another one in 2 weeks' time, concepts of downscaling not the 1st of March, but 8th of March, 8th of March. Now, what is detection attribution? A terminology coined by Klaus Hasselmann. So detection means we determine if observed variations are within the limits of variability of a given climate regime. Of course, you can apply it also to modeled variations. If this regime is undisturbed, then the limits of variability are given by internal variability, of which ENSO, NRO, and so forth are part of. If they are not within this limit of variability, then there must be an external cause foreign to the considered regime, or several of them. Then, if we have arrived at this conclusion, then we start with the attribution. That is, we determine a mix of plausible external forcing mechanisms that best explains, whatever that means, the detected variations. These concepts were introduced by Klaus Hasselmann in two papers, one in 1979 in a somewhat obscure publication, and rather complicated and hard to understand, and in 93 in the Journal of Climate in a really very clear and wonderful way. So if you want to read what he meant, go for the 93 paper. If you try the 79 and find it too difficult, just give up. So the issue is to deconstruct a given record with the intention to identify predictable components. Predictable means it's either natural processes which are known of having limited lifetimes, such as ENSO events, or man-made forcing processes which are subject to decisions such as greenhouse gases, urban effect. Of course, these words are differently understood in different social and scientific quarters. And the issue is also to help to discriminate between culturally supported claims and scientifically warranted claims. You know, I've just as an illustration here on the right-hand side is a time series. Actually, it's the ice coverage in the Baltic Sea, and different interpretations. How to look at that? Is it a trend? Do we see oscillation? Do we see a regime shift, or do we just see noise? Now, issues. Noise is nuisance, masking the signal. Variations are ubiquitous in the climate components, in particular in the atmospheric and oceanic dynamics. And on the right-hand side, I have a diagram which I showed before from Mitchell 1976. So that was from the really early times of modern climate sciences, showing a few spikes related to deterministic cycles, but otherwise a full spectrum. It means variance associated with all timescales in this range. Some variations are externally forced, such as the annual cycle, but many are not. And so they are unprovoked by external factors and present a kind of smoke without fire. And this is sometimes called noise. The interesting thing is the noise is constitutive for atmospheric and oceanic dynamics, but hinders the identification of causes and influences. So noise has a dual role, and this was introduced into our science by the other important paper by Klaus Hasselmann, 1976, stochastic climate models. And we also later, how many years, 25 years later, had a paper on the role of noise in the climate system in a collection in Mathematics Unlimited. Here, the mathematical concept of stochastic processes has turned out to be powerfully describing such noisy variations. So stochastic processes, randomness, are all mathematical concepts which are useful. Now, often people think that an anthropogenic signal is assumed to be in operation when trends are found to be significant. There's something to say to it, namely, if the null hypothesis is correctly rejected, and in most cases it is not, then the conclusion to be drawn is, if the data collection exercise would be repeated, then we may expect to see again a similar trend. So, for instance, if we look at Northern European warming trend April to July as part of the seasonal cycle. So we find a warming April to July, and we would also find it to be significant if we have many of these segments. But this significance does not imply that the trend will continue into the future, beyond the timescale of serial correlations. And indeed, September is usually cooler than July. So that's a limited value of significance of trends. Another issue is, where does the stochasticity come from? And it is a mathematical construct to allow an efficient description of simulated and observed climate variability. And in case of simulation data, this is internally generated by a very large number of chaotic processes. If you repeat the same calculation, really identically, with the same computer, with the same compiler and all this, then you get the same numbers. So there's no uncertainty in that. But if you just vary a little thing or do the same calculation on a different computer, then you get a different development. And on the right-hand side, we see an illustration of how this randomness can be generated. On top, you see two realizations of a nonlinear process, the so-called my process. And if you add 10 of them together, then you get in the middle diagram, and I'm not sure which of the two lines, so you get seemingly random variability with the distribution given at the lower diagram. So even though in principle the curves is deterministic, because it can be reproduced if we start with really identical conditions or run with identical conditions. But in the end, if we have a sum of very many of them, we cannot discriminate that from the mathematical, from something constructed with the mathematical concept of stochasticity. Indeed, if you look at random number generators, they are also deterministic. So you can generate the same random numbers if you really do it in the same way. But so what we should just keep in mind is the mathematical construct of randomness is an adequate concept for describing features resulting from the presence of very many chaotic processes. This is very different from a system when you have just a few or one chaotic process, like the Lorentz system or so. Now, the concept of detection attribution, and this is what Michael Schenk did. So let's assume that we have this situation. Actually, we have just seen Downton Abbey on Netflix, and somehow all this could have happened there. So let's assume that somebody finds a seemingly lifeless person and is surprised what to do about it. And so first we have to find out, is she really lifeless, or is she just pretending, or something of that sort? So this is the first step. Is it real what we see? Then usually a doctor is called, and the doctor has to decide, is she really dead? And did she die because of a broken heart or because of poison, for instance? And the poison would mean there's a crime, while a broken heart is also said, but it's maybe more natural. Now, if detection means then that the doctor finds out it is actually done by poison and not due to a broken heart. And this ends the role of the doctor. Next step is that the police is arriving at the scene and is examining the evidence, and in particular also asking witnesses of what happened. And if the police is good, then in the end there will be evidence or indications that a certain person was involved in the poisoning of the lady. And in this case, so that the police can say, oh, it's this one. Of course, there is something what we call in German Restzweifel. Now, let's first go to the manifestation. Is the lady really dead? And so I have one example here. These are the total losses per year from Atlantic tropical cyclones in 2005 dollars for, I forgot to add here where I have it from. It's from a paper by Roger Peter Jr. And we see that the damages have increased dramatically, really very strongly. And obviously, in this case, so we have something which is worth to be discussed. Another one is from the Sturmflut in Hamburg. It's a bit older, but I should update it sometimes. But what you see here is beginning in 1760 until 2000, storm surge heights in Hamburg. And whenever there's a yellow little, not whatever, on top of the bar, we had failure of the dike system, and the flood did not rise any further because of the failure of the dike system. So we have this regularly until 1825. Then the Senate decided that we should increase the dike height to the new green line, which was 5.70 meters above whatever NN means. And it obviously took a while, and in 1850, I'm not sure what, we had one more failure of dikes, but after that, nothing. I mean, then really comes an interesting period, almost 100 years. The surge heights were considerably lower than what we have seen before. If that is real or not is something else. But then in 1962, that is 60 years before almost today, we had the big disaster on the 17th February 1962, where the 5.70 meter high dikes were breached. And since then, we had more and more very high storm surges, the biggest one in 76, and I'm not quite sure how what the next 20 years brought, but not an ongoing massive increase. So here's also something to be considered. So this is not due to insufficient recording or anything of that sort, but the data are at least mostly robust, and we have something to think about. Here we have the global mean temperature, and this is, we have different sources here, a red curve, a green curve, and a blue one, and they're from different sources, and so they all describe the development of the global mean temperature. And we see that these curves essentially tell the same story, even though there are some differences, say in the 1950s, but essentially this means there's something real. If we go then to my favorite region, the temperature increase in the Baltic Sea region, and on the left you see what I mean with that. No, the North Sea is not part of the Baltic Sea region. And here we see, if we look at two data sources, CRU and EOPS, what the temperature increase of the different seasons is, and we see it's really, there was a considerable warming in of the order of 0.4 or something of that sort, or maybe even more degrees per decade in these 30 years. So the absolute warming is more than a degree in many cases, and it's relatively uniform. So in this case, I would say, yeah, we have something real. We have something where we've checked the data, and it's not an artifact of how the data have been collected or how they have been recorded or how they have been manipulated. Now let's go to the detection and cases. So now it is the task of the doctor who has to decide, is it a natural cause or is it not? And so we do that by using a test of a null hypothesis. So we ask if ST, that is a signal to be examined, the change to be examined, is that from a given probability distribution characterized by a certain mean state and covariance matrix sigma. And so in the lower two little diagrams, you see sketches for one-dimensional situation and two-dimensional situation. And so we ask, is our present state, is that in the margins of the distribution or not? If it's within, it's not in the margins, then we'd say, okay, it still could be related to to natural variability. While if it's outside, then we'd say, no, the evidence is that very likely it is not. Even though, of course, it is a subjective choice to say when the margins begin and when not. Now, if we go after the issue of the global mean temperature, this is the study, an approach suggested by Armin Runde and his workers. And here we see a time series of the temporal development of an M-year mean temperature, global mean temperature, and centered around a year I. The difference between two of these mean values separated by L years, and the top diagram is 20 years, and the lower one is 100 years. And then we also have, all this is normalized, and we have thresholds, 2 or 2.5 or 3 sigmas, as given by dashed lines. And the dashed lines model is Gaussian long memory processes fitted to various reconstruction of historical temperature. So we have here Mike Mann's work, but also of the climate skeptic John McIntyre, but also others like Moberg and Jones. And the result is almost the same. And so, namely, that we have in particular in the late years, we see that we are beyond even the 3 sigma level. So if we have just a 20-year time difference of 5-year means, this is less clear. But in case of a 100-year difference or 30-year means, we can say that there should be little doubt about the reality of non-internal processes beginning in, say, 1985 or so. That is, there's something to be explained. There's something going on in the global mean air temperature which needs to be explained by external factors. In detection, we may conclude detection has been achieved with robust methods. So there's nothing sophisticated in this. And so that means in the 2 diagrams of the IPCC AR5, there is something which is not due to internal reasons. Of course, the caveat is the natural variability correctly estimated? So that's something we cannot definitely answer at this time, but we can say it is plausible that we did it well. In case of the Baltic Sea, I've shown that before. We have here the change of the temperature averaged across the entire region for different seasons, DJF and so forth. And the gray bar is what the temperature change is in Kelvin per decade. And the red whiskers indicate what we think 95th percentile of non-greenhouse gas variability may be. It's derived from a 2000-year paleo simulation. And last time somebody said quite rightly that it would be a pretty big assumption to think that this is what really is the natural variability, but that's the best we had. And so what it is we see that December, January, February, we have a clear warming, but there's a tiny little chance that this would also occur according to this paleo simulation under undisturbed conditions. But this is different in the other 3 regions, May, April, May, June, July, August, and fall, where the red bar does no longer include 0. That is, in these three cases, we have certainly a detection of a warming which is beyond the range of natural variations. Here we have something, and I should have added a few more details. In particular, I should have said what the mysterious M is. So here we determined how many it was noticed in the IPCC report number 5 or so, or maybe 4, that we had a clustering of the warmest years in the last 17 years, and this was something of the order of 13 or 14 or so. And so the question was, how probable is it that we have these? We have this now for regions, and then we can say the probability is usually something of the order of 10 to the minus 2, or 10 to the minus, between 10 to the minus 2 and 10 to the minus 1. But also smaller values, so that we have some chances to say, yeah, just by counting the records and the temperature record, that we have something which is very rare and thus should be explained by external factors. So this was the story about the detection. We can say this is something which is extremely rare and it should be explained by external factors. It does not imply by which. And so we come now to the detective arriving at the crime scene. And so if we start with the storm surges in Hamburg. So we have something to explain. And one explanation is this, namely we look at the difference between the peak heights of storm surges in Cuxhaven and Hamburg. And I guess I don't need to explain where these two locations are here. So we see that we had until about 1960 a difference of, let's say, 40 and less centimeters. So in Hamburg, the storm surge was 40 centimeters and or less than in Cuxhaven. And since about 1980, it is more of the order of 100 or maybe 90 centimeters or so. And from the 1960s to the 1980s, there is a more or less linear increase. And if you look a bit more careful, then you would possibly dare to say this trend began in 1962 after the storm surge, when all the waterworks began in the Elbe, which transformed the Elbe. And the effect of this transformation was that the storm surges became higher in Hamburg, and also not only the storm surges, also the tides. And the tide wave and storm surge waves would move much faster from Cuxhaven to Hamburg, namely 1 hour, than it would need 1 hour less. So the increase of the storm surge heights in Hamburg and the original diagram can be to a large extent be explained by the other diagram, which means that the transformation of the tidal river, that is deepening and dredging of the river, but also efficient coastal defense measures, led to the increase of the observed storm surges, and not, as some people had suggested, would be a sign of climate change. By the way, this was suggested also by very visible and honorable climate scientists such as Hartmut Grasse. Now, what about the other issue, the losses of the economic losses from Atlantic tropical cyclones in the United States? So I had shown the top diagram before, and then this research group from the United States made an estimation of how much damage would have happened if the number of people and values along the coast would have been constant. And that obviously there's much more value amassed in Florida, say, Florida, than previously, and also much more people live there now. And so if you take that into account, you get the lower diagram, then you suddenly see, no, the trend is gone. So this would be one explanation, but not necessarily the weather. So this was a diagram which was published in the IPCC 2007. It has been updated, but it's still valid. I'm using it because it's a little simpler. And namely, it shows efforts to try to simulate what the temperature development as given by 10-year means would be if we have only natural factors, so that would mean that we have only, say, solar variations and volcanoes and internal variability, and the result would be the blue band. The actual development based on temperature measurements is given by in terms of 10-year means, is given by the black line. And the black line is well covered by the red band, which is displaying what models suggest the temperature development should have been if we actually had greenhouse gases and aerosol changing. This is, I think, rather convincing, and that's a key diagram in the history of climate sciences, namely that it shows, yes, we can explain the ongoing warming if we add the human-made factors. And so far, we have no other hypotheses of alternative drivers. Of course, it could be that we specified other drivers like the sun, not fully correctly, and things of that sort. So there are, as I said before, Restzweifel is always in science, but this was considered by most people as a pretty good evidence that we see a warming, which at this time we can explain only because of the elevated levels of greenhouse gases in the atmosphere. So in this case, we have an attribution. This person is the killer. But it could be that there are several killers. And this is a diagram which was from the 1990s. And this shows as a line, on this noisy line, the development of the climate system for observed 50-year trends in June, July mean temperature is given by two detection variables. I mean, these are variables which are typical for instance, CO2 for a CO2 change, and the other one is CO2 and an aerosol change. I hope at least that it is so. And it shows that in the beginning of this period, we would say, well, could be natural variability, but also solar. But more and more so, if we go forward in time, we cannot say this anymore. We could possibly sometimes in between have said it's mostly CO2, but all the time it was consistent with both CO2 and aerosol presence in the atmosphere. So we would say climate change, in terms of the global mean, would represent itself as a response to CO2 and aerosol, plus, of course, internal variability. A similar exercise did we, that is Armenia, Bulgaria, for southern, the northern part of South America, and that's the strange map you see in the top right. So this is, you see mostly Brazil and Peru, and so it's cut off north of Montevideo, or Uruguay, and also the northern states are somewhat cut off. Anyway, here we talk about observed precipitation trends in this tropical sector of South America, and this is August to October, and here we look at the period 83 to 2012. And so we were asking, are there changes detectable at the 5% level locally? And whenever we have brown things, then we would say, yes, it has become much drier than compared what we would expect from only natural variability, and the green one has become more wet. So the green ones are small areas, and you could say that's exactly what you expect from a statistical test, that even if the null hypothesis is valid, you have small regions, say of the order of 5%, where you have evidence that something may have changed significantly, but that's part of the design of tests. But the blue area is larger. Here we have now we have attempted to use two forcing mechanisms to describe things. One is land use, and the other is greenhouse gases. And here we again have two detection variables, one for greenhouse gases taken from such climate model scenarios and the land use change. And what we see is that the present change, which is given in terms of the two detection variables, is something like 1.5 and 1.2 or so, is inconsistent with the zero. That is, it cannot be explained only by internal variability, but that we really need both the land use and the greenhouse gases to say it is to explain the ongoing change. We thought that was pretty remarkable. We would also have been able to attribute it only to greenhouse gases by just neglecting the land use. But if we add the land use, our ability to explain it has become considerably better. So neither greenhouse gases alone nor land use are really sufficient to explain the recent change. So this brings me to the end of this seminar to discuss a little bit, again, what we may have learned. So the dimensions of DNA is statistical rigor we have with the detection, but we only have plausibility in terms of the attribution. Because in case of the detection, we reject a null hypothesis, which is a strong statement. And in case of plausibility of attribution, we just do not reject a null hypothesis, which is a relatively weak argument. D, the detection depends on the assumptions about internal variability. And of course, if people say, I don't believe that you have estimated the internal variability correctly, then what can I say? I mean, I cannot disprove such a claim, but on the other hand, my opponent cannot disprove that my estimate is right. You can just say it. A, the attribution depends on model-based concepts, usually. And so it may be that you say, oh, the models are maybe not the right ones. And this situation becomes even more significant when we talk about event-based attribution than it is fully based on model-based concepts. And therefore, I'm not 100% happy with this concept. Thus, we have remaining doubts beyond the specified ones. We have to keep that in mind, but I would not say that I would be inclined to relax on my conclusions. Now, how do we determine attributability? We can use the limited empirical evidence from instrumental observations or analyses, possibly after suitable extraction of the suspected non-natural signals. That's what we did when we started this. We can also look at long control simulations with quasi-realistic climate models, such as this 2000-year paleo simulation. But we could also, and this has done not very often, project the signal on a proxy data space and then determine the statistics of the latter from geoscience indirect evidence. That is, we would say what we have seen in warming should be reflected by, say, tree rings in this and that manner. And then we compare these changes in tree rings derived from temperature change with the statistics of tree ring growth or composition. That would be nice to do, but I'm at least not aware that this has been done in a systematic way, but it would be more convincing. With the attribution implies the assertion of the consistency of a change with a set of expected responses. So it's a statement about possibility and plausibility. But is there only one set of plausible attributable causes? This is difficult to say. If we identify a cause A as attributable to a change, does it mean that we have to exclude B as a driver? And then finally, it may be that we do not know all possible causes which could attribute to a change. And just to make ourselves a bit modest, think of Lord Kelvin's claim, who said in about 1900, there's nothing new to be discovered in physics now, which obviously was not the case. But I mean, I guess Kelvin was a very intelligent and smart person. And if he fails to such a claim, then who would protect us from doing the same? Now, to sum all this up, the detection attribution concept was introduced by Hasselmann in 1979 and 1903. It has become a key concept in the assessment of the IPCC about the state of the climate system under human pressure. And its value was emphasized by awarding the Nobel Prize in Physics to this gentleman. Global quantities, in particular, have been shown to be influenced by external factors, among which elevated greenhouse gases must be a dominant driver. This has not been done extensively for regional statistics or regional changes. And one would expect that the concept will be used for assessing change in the regional states as well, assess changes in impact conditions, and maybe geoengineering once something of that sort would be tried out, or maybe only in modeling studies.